If you've ever taken Calc 2, this scripture on screen will probably look very familiar to you. If you don't know this, it's known as the fundamental theorem of calculus, and it's also the way we compute definite integrals. If you don't know what a definite integral is, it's just the area under a curve represented by a function from any 2 points on the x-axis. So for example, this is the graph of f of x equals x squared. So then this area here would be the area under this curve from x equals 2 to x equals 5 of x squared. And the reason we have, oh my god, and the reason we have we're multiplying x squared by dx here is because essentially all we do when we integrate is we break up the area into a bunch of infinitesimally small rectangles, and then we're adding the areas of those rectangles all up. Here's a close-up of one of those rectangles, so the area here would be f of x, which is x squared here, times dx. I also have to clarify, when we have something like this, where it's a capital F instead of a regular f of x, this denotes the antiderivative of the function. So if we had this function f of x equals x squared, capital F of x, or the antiderivative, would be x cubed on 3, since the derivative of x cubed on 3 is x squared. Another notation we use for the antiderivative is this this is the most common notation. In fact, you'll actually never see this notation with the capital F. It's only used in this proof mainly, but there's also negative areas and stuff like that, but we don't need to delve into that for this video. So now, since we've clarified all of TS, now let's imagine a function of t, which is just 10. So it would look like this, just straight line. I'm trying to make it as simple as possible, but I'll generalize it later, to include all cases. Anyway, imagine this function, and we have a point here on the t-axis called x, and there's a line going from the t-axis from x to, and what this line here is doing is it's sweeping out an area from 0 to x under this line here. We'll call the area, this gray stuff, a of x, to represent this area that's being swept out. And since it's sweeping out an area from 0 to x, we can write this as an integral, which is this. Now, the derivative of a of x is essentially just asking how much area is being swept out under this line up here per second, since the derivative is just a rate. And that would just be 10 per second, because for every rectangle here that has base 1, the height is 10, so that's just 10 times 1. In fact, if we used any time interval, it would still be 10, because, for example, if you use 0.1, it would be 0.1 times 10, which is the area, per time, which is still 0.1. So those two cancel out, and we still get 10. And even if we had infinitesimal base, they would still cancel out and we get 10. So now we know the derivative of the area function is 10, which is also the function's height, which is f of x. This is very important. And now, since the derivative of the area function is f of x, we can now say that the area function, this integral here, is the antiderivative of f of x. Now, the last piece of information that we need is, let's say we wanted to find the area from a to b under f of t. We could find that from first taking the area from 0 to b and then subtracting the area from 0 to a of that. You can see that here. And on paper, that looks like this. And using this right here, we can rewrite this as this. And now we link these two, to get this, which is the fundamental theorem. Fundamental. And this works for any function. Let's say we have a function f, just any old function, just any random function, and we cut the area under it up into tiny little rectangles, infinitesimally small. This down here would be the rectangle, and so the rate of area per time, here the time is dx, and the area is f of x times dx. So those two cancel out, and we're just left with frick! And we're just left with f of x. So now we know this works for any function. When I first saw this formula for area under curve, I was flabbergasted. I thought it was so weird that the antiderivative of a function was so crucial to its area. And this idea of taking stuff, infinitely cutting it up, and freaking adding up the cuts isn't just special for like just area under curves. They can be used for finding the arc length of curves, whether they're represented parametrically or just regular functions. And can also be used for volumes and hypervolumes and even a lot more. Like even freaking like quantum and stuff like that, bro. Like, dude. Moral of the story, Newton and Leibniz, I love them. I love them a lot. Alright, bye.